we've arrived at the point in our advanced 2D problems where we're going to take on our first intersection problem. So this is an old classical problem in geometry. You're given two extended lines. They intersect in a single point most of the time, unless the lines are parallel. And so any good system of geometry can be measured on how easily it is to solve this problem. And also, I think we're adding a whole new metric to geometry, which is, can we develop a solution that handles every possible case of input? And we'll keep to that standard as we move forward in all our problems. Okay, so we'll be charting a little bit of new ground here, because even though this problem goes way back to the Babylonians and algebra, the way we're going to solve it is fairly new. And so instead of working with traditional algebraic equations to represent the lines, we've got this new vector line equation, P dot O equals L. We've got the lines coming in represented numerically with their orientations and their locations. So I think one of the fun things about this problem is knowing that you'll be one of the first people, or first in a group of people, to be solving intersection of two lines this new way. Well, let's start by looking at the problem definition. I'm looking over at the right-hand window. So we're given two lines, the yellow L1, magenta L2, and we're asked to compute their point of intersection. Well, that's going to be this point right here. And we're supposed to signal non-intersection degeneracy. Oh, okay. Well, obviously two parallel lines are not going to form an intersection. So that is our degeneracy condition. And we could actually start with that, and you look through your past work here. Right here we have a module that decides if two extended lines are parallel. So why don't we just get this out of the way? Okay, so now all that's left, and I'm being a little facetious saying all that's left, is to calculate this intersection point. And so it's not real obvious where to start with this, and it looks a little bit complicated. So one thing we've done in the past when confronted with that kind of complexity is asked ourselves the following question: is there a simpler special case of two-line intersection that we might be able to solve? And in fact, is there a special case we could get to through a transform? Okay, well, we don't have any positional information, so we're probably not going to be able to use a coordinate translate, but both lines present directional information through their orientation vectors. And we could use one of those to guide us through a coordinate rotate. So we've got that method, we got the graphics. Why don't we explore what that would look like? So let's pull out a coordinate rotate line. This is the module you just solved in the last challenge. And we're going to take line L2, we're going to take the orientation from L2 and use that as the new x-axis. And based on the theory, this should make this line stand perfectly vertical. Well, there it is. And in fact, if we move L2 around, you see how the transform line is always vertical, and the run direction is always up. And All we're changing is the location of the magenta line from the origin. So it can go negative and it can go positive. Okay? Well, if we were going to transform the entire problem, we'd have to also put L1, the yellow line, through the same transform. Well, let's do that. So we'll use the same L2 orientation for the new x-axis, and we'll push line L1 through that, and you see where it comes out. So L1 comes out over here. And it's going to be worth it to explore this simple case for a couple of reasons. First of all, one of the lines has been greatly simplified. It stands vertical. And the other thing we can say about the magenta line after its transform is we know that this distance here is going to be the same L value as in the original line. Why is that? Well, because that distance from the origin does not change when you rotate. And so we already know that the coordinate of the intersection point in this coordinate system with these two lines, we already have a solution for its x value. All right, well, let's go and sketch this simplified special case. Let's go solve that. And then we'll come back and we'll solve the general case. And let's just prepare our workspace here. This was just for a simple demo, so we don't need these anymore. And why don't we bring out the O and L for all two lines. So now we're in a state of readiness to work on the problem when we come back to this point. All right, well, let's start sketching. This will be the intersection of two lines, intersection point of L1 and L2, where it's going to be a special case where L2 is going to be perfectly vertical. All right, so now we've got to have our two lines, and I'm just going to make these red and yellow. And so we'll start with L2. L2 is going to be vertical. Label it. And now we're going to make L1 come closer to the origin. Go just like that. L1. And the result we're looking for is this intersection point here, and we'll just label it I. Okay, so let's write down our givens and our result we're looking for. Okay, now these lines, how are they going to come to us? It's not going to be y equals mx plus b. These are going to be in the vector line equation form, where each line is represented by its orientation, which is O, and its location L. So we'll just label these as, all right, so let's say we're going to receive L1, and it will consist of the orientation 1. So we're going to write this as O1 dot x O1 dot y. There's that direction vector. And O1. Okay. We can put these in a larger bracket to show that's just comes in as one object. All right, do the same thing for L2. Okay, so now this direction vector, the orientation of L2, since we know the line's vertical, we can say this will be something like this. It'll either be plus or minus 1, 0, and L2. Okay. All right, so the thing we already know about this intersection point, I, is its x-coordinate, right? Well, that's because all the points on L2, what are their coordinate? Well, we know that this was brought into place by a coordinate rotation, and we used L2's, we're going to have L2's location, which didn't change going through the rotation. So let's now draw in, this is L2. So we already know half the result. We know the x-coordinate of our intersection point. So let's write that down over here. This will be pseudocode. All right, so I'm going to write it in white. So we know that the x-coordinate of the intersection point is equal to L2, one of our givens. Okay. Okay, so now we're going to approach this using some algebra. So looking at the red line, all we need now is to figure out the y-coordinate of the intersection point. And we're going to do this with some algebra using the line equation for L1. Okay, because all the points on L1 obey its line equation, or its vector line equation, and we're going to use that. Now, since we already know the x-coordinate of the solution point I, we've got a line equation for L1, that should be enough information to allow us to solve for the y-coordinate. Okay. So let's proceed to, let's just start with the general line equation in vector form. P dot O equals L. This is going to apply to line 1. And furthermore, we're not interested in all the points on line 1. We're interested in just that one point, I. And that point is on line 1. So immediately we can say I dot O equals L. And since it's line 1, it'll be the L value for line 1, L1. This will be the orientation for line 1. Okay. we're going to now expand the dot product. So if you remember the dot product, you multiply the x's, you multiply the y's, and then you add them together. So let's break out the thing here, the dot product, into its expanded form. So what we're going to get is I x coordinate times O1 x coordinate plus I y coordinate times O1 y coordinate equals L1. Okay. Okay, so that's just taking this dot product and expanding it out into its scalar multiplies and adds, right? All right, so now we can substitute because we do know the x-coordinate of I already. That was in our pseudocode up above. So let's substitute in L2. L2 times O1 dot x plus the y-coordinate of I times O1 y-coordinate equals L1. Okay? So we've only got one unknown. Everything else is known in this last equation. The thing we're trying to solve for is the y-coordinate of I. But all these other numbers are in our givens, right? So L2, O1, and L1, those are all in our givens, right? You can go up and look at them. There they all are right there. There's four given quantities. These are going to come in as hard numbers. Those four things are going to come in as hard numbers. So we've got an equation here, a linear equation, with all hard numbers and just one variable. So that says through algebra we can solve it. All we got to do is manipulate this equation to put the I dot y on one side. All right, so let's see. The first thing we'll do is subtract this thing from both sides. So now we'll just have I dot y times O1 dot y. We're moving the other thing, so we'll have L1 on the right side minus the thing we subtracted, L2 O1 dot x. Okay? And we're almost there. We just have one more step. So we just divide both sides by this thing. And we have I dot y equals L1 minus L2 O1 dot x quantity divided by O1 dot y. Okay, so there's our solution. That gives us the y-coordinate of the intersection point. We already had the x-coordinate, so now let's write the whole thing out for I. So I, point I, the intersection point, equals, the x-coordinate was just L2, and the y-coordinate, we see just right up above here, L1 minus L2 times O1 dot x divided by O1 dot y. Okay, so there's our intersection point. Now, just taking a look at it, it can be calculated. Everything on the right side are given numbers, right? These will all be these four numbers. Remember, we looked up here, underlined them. We got four hard numbers that come in with our two lines as their features. And this is how they're arranged in the computation to calculate point I, the intersection point. All right, so now this is something that will be fairly straightforward to implement with a data flow. Okay, so we've already shown that we can solve the special case of intersection of two lines, where one of the lines is made vertical. So now let's tackle our strategy for the intersection point of L1 and L2. And this will be the general case. So this should be able to solve any two pairs of lines. All right, so what we'll need here is two sets of axes. So one on the left, one on the right. Okay, so this one's going to be our x and y. These are your original problem coordinates. Over on the right, this will be coordinate rotated. So these will be transformed coordinates x prime and y prime. So let's start by setting up our problem. And I'm just going to draw two lines. Now the red will be L1, yellow L2, and the result we're looking for is this intersection point I. Okay, so basically all we have to do for this general case is to transform it into the special case, which you've already solved. You'll know how to compute the solution to it. And so what we'll be doing, let's draw an arrow here. So this will be a coordinate rotate. And we said for the special case we wanted L2 to stand vertical. So what that means is, we just draw in the orientation for L2. That thing will become the new x-axis. So we'll be using L2 orientation to define our new x-axis. Okay, and so now we can redraw. And so I'm going to try to get my distance from the origin for L2 about the same as it is on the left side. We'll call this L2 prime. And a red line Comes much closer to the origin. Makes an angle about like that. This is L1 prime. And intersection point, call this I prime. Okay, so we know we can solve the problem on the right. So when we finally get I prime, we're not done. We have to back transform that point into the original coordinates. All right, so let's draw yet another arrow here. Just showing that we're going to have to come back with our result. Coordinate unrotate. The point we're going to push through the rotate is I prime. And what we're going to get out on the other end is I. And then we're going to use the exact same transform control, which is the orientation of L2, to come back. Okay, and I guess we could also, just to make this complete, our givens are going to be L1 and L2, and our expected result at this level will be the intersection point I. Now, there is a degeneracy case. We all know what this is. So this is going to be L1 is parallel to L2. And we will want to weed out that case before we even send it over to the right side to be solved. And so this looks pretty simple. We've really simplified this problem through the coordinate rotate. We've transformed the original problem, which is daunting and hairy, into a simple case, a special case that's simple to solve, just using some algebra with the vector line equation. And then, again, we come back through a back transform. So a lot of the complexity of solving the problem on the left takes place through this return or back transform. Okay? So we've got one more step, and that's going to be to revisit our pseudocode and make it so that it's knowledgeable about having a transformed line. Okay, so why is that? Well, on the left, look at L1. Okay? On the right, look at L1 prime. So that line is going to have to be computed. L1 prime is going to have to be computed. So let's write in some pseudocode before we leave the general case. So we'll say L1 prime equals coordinate rotate L1. And we'll be using L2's orientation to control the coordinate rotate. So now I think we're done here with the general case. And we can just do that last step I mentioned of rewriting our pseudocode to show that it's L1 prime. We have to use in the special case. Okay, so the last step in planning our solution for intersection of two lines, we're just going to modify our special case calculation to handle the general case. Our special case calculation was I L2 is the x-coordinate. L1 minus L2 times orientation 1 dot x divided by orientation 1 dot y. Okay, so then our general case, we just need to modify this, recognizing that L1 will be coordinate rotated, so it'll be working with L1 prime. Instead of L1, and our result will be I prime. So we can now say this will be I prime, and L2, that didn't change under the transform. Okay, so here we have to be careful. So we are going to transform line 1. So L1 becomes an L1 prime. And we have to be careful here with the orientation vector of O1. So it's going to be O1 prime dot x. And we're going to divide by O1 prime dot y. So we're just making sure that we're using L1 prime is equal to O1 prime dot x, O1 prime dot y, and L1 prime. Okay, and actually, since when lines go through coordinate rotation, their location values do not change, we don't have to use the prime value for L. It'll come out the same number, so we can just remove the primes for the location of L1 prime. And essentially now we have everything we need here. And so here's our pseudocode for computing I1 prime. And then of course the last step we already showed, but I'll write it again. The solution I will, oops, oblige a coordinate unrotate, or I prime, and line 2's orientation. So that looks like it. Maybe we're missing one little thing, and that's at the very beginning we have to compute line L1 prime, and that'll be a coordinate rotate of line L1 using L2's orientation. There we go. Now we've got all our pseudocode. So in fact, we can now say in the order these are going to be done. This will be the step 1. This will be step 2. And this will be step 3 in the computation. So with that, take your time, be methodical, keep this in front of you, and you can now go and carefully implement your data flow for the intersection of two lines. Wow, well, that was quite the endeavor, and if you're looking at the same phenomenon on your test screen I'm looking at, then kudos, because you deserve a lot of credit for effort on this one. Not only diving into the theory of how you would compute the intersection of two extended lines represented the way we're doing it with orientations and locations, but just also the data flow was fairly involved just to get all the parts in there working in the data flow. So again, this is a major accomplishment, and the one thing you would want to additionally test before leaving this testing phase here is to just set up your two input lines as being parallel to one another. I know it's a little tricky, takes some eye-hand coordination, and there we have it. So our degeneracy is being reported, and so we'll be working on some other intersection algorithms that are kind of equal complexity, things that you would never have seen in a classical geometry education. This one you do using techniques such as subtracting equations from each other to eliminate a variable. We're essentially doing something very analogous here by pulling a coordinate rotate on one of our two input lines. So we're bringing the other line into a coordinate system in which the other line is perfectly vertical, and that greatly simplifies finding the intersection point. So kudos again on this. This is not easy. It's a major accomplishment, something few have done here before, and so big pat on the back. Wow, I don't know about you, but when I first solved this intersection of two lines using the data flow system, I got a real rush, real sense of power. When you do this kind of problem solving, you realize that there's more than one way to skin a cat. And fortunately, we have another tour guide here at the channel, and he's going to show you a completely different approach to the intersection of two lines. His name is Tour Guide A, and I find his approach very, very interesting. So I hope you'll check it out. Here he is, Tour Guide A.
Hello everyone, I'm Tour Guide A, and in this series of videos, I'm going to be showing you a different approach to intersection problems from what Tour Guide F has already shown you. So, with that being said, let's jump right in. In this video, we're going to be finding the intersection of two lines. So, in this diagram, you'll see that we have two lines, as you might expect. The blue one is labeled L1, the red one's labeled L2, and their intersection point I is in yellow. Alright, so we're given the same information about these two lines, but we'll start by looking at the attributes of L1 and just going a little bit in depth into what each of these attributes mean. First we have O1. This is a direction vector that runs perpendicular to the run direction of L1. And then we have L1, lowercase l1, I must say, which is the length from the origin to the line L1 along this direction of O1. And we also have these same attributes of the line L2 as I mentioned previously. Cool. Well, let's get to solving. So in order to get a basis from which we'll construct our solution, let's take a look at this visual. You'll see that the vectors v1 and v2, which have the same run direction as their respective lines, form a parallelogram. From this parallelogram, we see that v1 plus v2 is equal to I. This means that we have to solve for v1 and v2, and then we'll get I. Alright, let's start by solving for v1. Now, we need 2 bits of information to find this vector, namely its direction and its magnitude. So the direction of v1 is the same as the run direction of L1, which is the direction vector O1 rotated 90 degrees clockwise. Cool, that's half the puzzle done. Now, to find the magnitude of v1, we have to look at the angle theta between O2 and v1. So from our diagram, it's pretty clear that the cosine of theta is equal to L2 divided by the magnitude of v1. But you can also note that O2 and the run direction of L1 are both unit vectors. So what that means is that, well, cosine theta is also equal to O2 dot run direction of L1. Now we can use these last 2 equations here to solve for v1's magnitude. I mean, I'll let you do the algebraic manipulation, but yeah, we can pretty evidently do so. Now we have all the puzzle pieces to solve for v1. So this is our generic magnitude and direction form of a vector. And so for v1, since we have all the information, we can just substitute it in, and there we go. That's v1. Now, we can apply the exact same logic that we just used to solve for v1 in order to find v2. Now, here are the steps, and you can verify independently that this is the correct answer for v2. Alright, so now all we have to do is just put everything together. So we're going to go back to this diagram with v1 and v2 in a parallelogram. And remember that our original equation was v1 plus v2 is equal to I. Now we've already solved for v1 and v2, so we can just substitute expressions for those quantities into our equation here. And there you go. We have solved for I. We have this neat little expression on the top right of your screen here. That is the equation for I. Now we're going to look at the degeneracy case. And in this case, L1 and L2 never intersect. And because we're dealing in 2D geometry here, Euclidean geometry states that this means that L1 and L2 must be parallel. So in turn, that means that these 2 lines share the same orientation direction. And so what that means is that the dot product of O2 and the run direction of L1 is equal to the dot product of O1 and the run direction of L2, and both of those are equal to 0. So that means we have a divide by 0 error, and unfortunately, this doesn't get flagged as degenerate within the scope of our algorithm. So what we have to do is we have to think about, okay, when are 2 lines never going to intersect? And as you might remember, I just said a couple seconds ago, this happens when the 2 lines are parallel. So we just have to add a check, a module that asks, are these 2 lines parallel? And if they are, then report degeneracy. Okay, so that's curtains for our first intersection algorithm. Now, you'll notice that the approach we used for L1 and L2 here was a little bit different from what Tour Guide F already showed you, because of 2 reasons. First of all, it was symmetric, meaning that the algorithm had the same steps if you viewed it from the perspective of L1 as if you viewed it from the perspective of L2. Secondly, it was an algorithm that did not use any transforms. So that means that the original problem that we got was the problem that we solved. We didn't simplify the problem really to any simpler case. So that's goodbye for now, and I'll see you in a couple of videos when we talk about the intersection of circle and line.
That is really cool. So, yeah, what I think Tour Guide A has done here is original work. I'm not an expert on the literature, but I've never seen this problem, the intersection of two lines, approached as a vector sum of two vectors. So I find that very original, and I'd be curious if you have ever seen this approach published before. Please leave a comment below. We're just going to move on here now to something that goes back into Pythagorean or Greek geometry, and what we want to do is develop a right triangle solver where, given the hypotenuse and one of the legs, it will crank out the other leg of a right triangle. So we'll see you over there.